Hello, everyone. Welcome to another wonderful day of chemistry. So last time we took a look at how we could examine ideal mixtures, where the intermolecular forces of both components of a mixture were going to be very similar. However, that turns out not to be the case for most of our real solution mixtures. In these cases, we tend to find the intermolecular forces for both of the components tend to be different than for the pure species. So for example, acetone is held together by these nice dipole interactions with a negatively charged oxygen, positively charged carbon, and they'll sit there and line up. Carbon disulfide is glued together by nice dispersive interactions, which will end up helping keep the system stitched together. Now, if I mix the two, well, it turns out the acetone will break up the dispersive interactions and the uh, carbon disulfide will break up the dipoles, and both cases will tend to be more volatile than expected. And this is known as a positive deviation from Raoult's law. And we call this such because the partial pressure for both component is significantly above where we'd expect to see the Raoult's line of ideality. This also means the total vapor pressure also for this mixture also tends to be much greater than for the ideal system of either base pure component. And this will be the case anytime we have these net repulsive intermolecular forces, or the systems will much prefer to be on their own than mixed together. We'll occasionally also run into a case where we have net attractive intermolecular forces, and in this case, we'll see a negative deviation from ideality, where the line of reality will be below the Raoult's line. But what we'll tend to see is note that we tend to have the best adherence to Raoult's law near mole fractions of 1. However, if we look on the other end at these very low concentrations, where each of our components act more as solutes, you'll notice we have a very large deviation. So what we're going to try and do today is build up a model that describes these low mole fraction mixtures and how we can describe them. Now, one of the best ways to do this is to treat the vapor pressure of a very dilute solute. Because in this dilute region, you'll notice that we tend to have a relatively linear region for a mole fraction of up to about 0.1, 0.05 to about zero point 0.2, depending on the mixture. Now, what we can do is we can go ahead and fit this nice narrow region to its own linear relationship, where we find a linear relationship in between the vapor pressure and the mole fraction. But now instead of the constant being the ideal vapor pressure, we switch it into something called the Henry's constant. So your book will go ahead and denote this as Kb because it's referencing the solute. In the literature, it's more commonly known as Kh for literally the Henry's constant. Now, the important thing here is the Henry's constant is, as a whole, tends to be experimentally determined, um, and it's often known again as this Kh. Now, again, it's worth noting that all mixtures won't necessarily obey Henry's law, and every mixture will start deviating from Henry's law when we get to a sufficiently high concentration. Sometimes this will be a mole fraction of 0.1 or 0.01. Sometimes it will hold all the way up to about zero point 0.2 or zero point 0.3. So you do need to know something about the solution to know what the case it is. But if a mixture does obey Henry's law, it's called an ideal dilute solution, because an ideal solution will hold Raoult's law the whole time. But if it holds a linear relationship for the dilute solute, then it's ideal for dilute. So, very clever phrase. But this is really what Henry's law is making use of. Raoult's law handles these solvents well. Henry's law is going to describe the solutes well. However, in practice, Henry's law, since it's mostly used to describe solutes, we're often going to, and we're looking at really the vaporization of a solute to forming a gas. It's more commonly written in terms of molality because molality is a lot easier to measure and use than mole fraction. But we will find in many of these dilute solute cases, we can go ahead and replace the mole fraction with the molality. But note when we do this, that will change the Henry's law value. Now, the most common case you're often going to look up and find Henry's law is going to be for dissolved gases. So these are going to be species with relatively high constants because they'll tend to leave solution fairly readily. So some of the ones that are most commonly reported are going to be things like CO2, hydrogen, nitrogen, oxygen. These are very heavily used in a lot of environmental chemistry because we do very much care about the concentration of both of these species in that dissolved state. And you'll find relatively common Henry's constants. But one of the things you have to watch out for is that Henry's law constants are sometimes given in terms of molality and sometimes in terms of mole fraction. And they'll never really tell you which one they're using. So as always, the real trick here is to look at the constants because they'll always provide those. And in this case, we'll tend to find the Henry's law constants will always have a pressure. And then if it's in terms of mole fraction, it will just be the pressure. If it's in terms of molality, we'll then have units of inverse molality. In this case, kilograms over moles. Again, if it's in mole fraction, it'll be just kilopascals. Also, be cautious. You'll occasionally also see Henry's law constants provided for the reverse reaction, at which point they move the Henry's constant onto the other side. And you can tell when that's the case because the units will be flipped. It'll either be inverse pressure or moles over inverse pressure, inverse kilograms. So again, when in doubt, always keep eye on the units because you may be using the wrong equation. And this will be something to keep in mind whenever you're using literature databases for Henry's constants. Now, one of the big advantages of Henry's law is we can use Henry's law and Raoult's law together to describe most liquid mixtures. Because it turns out, and we can really see this when looking at a mixture of chloroform and acetone. So acetone, again, as we said previously, is polar. It has a slight positive charge on the carbon, but a big negative charge on the oxygen. Now, if I mix this with chloroform, which has a large positive charge on the hydrogen, and then a diffuse negative charge on the chlorines, it turns out that the mixture tends to like aggregating together much more than acetone wants to be with acetone or chloroform with chloroform because it matches the charges better. Now, this is a rare case, but it does lead to a negative deviation from Raoult's law. And you'll notice that in both, that we can describe in both cases, for mole fractions above about 0.9, chloroform obeys Raoult's law pretty well. But below that, it deviates significantly. Similarly, for acetone, for mole fractions of acetone above about 0.9, 0.95, it also obeys Raoult's law pretty well, but it deviates significantly as a solute. So what we can then do is say, all right, if acetone is acting as a solvent, I can use Raoult's law. But if it's acting as a solute, then I need to use Henry's law. And we can see that it also obeys Henry's law up to mole fractions of, then again, about 0.15. And for chloroform, it obeys to mole fractions, again, about 0.1, 0.15, all fairly common. And so what you'll note is that we're able to stitch these together. When you've got a solute, you treat it with Henry's law. When you have a solvent, you use Raoult's law. Now, the trick, and again, we can also tell if we have a positive or negative deviation by comparing these values. If the Henry's law constant is lower, if the Henry's law constant is lower than the ideal vapor pressure, it means we have a negative deviation. If it's higher, then it means I have a positive deviation or it's more volatile. Now, we can use these to get a good estimate of what the actual full vapor pressure diagram looks like. But it's worth noting, we do see this kind of breakdown in the middle, where we have a tough time describing these mole fractions in between kind of 0.1 and 0.9. So for that, next time we're going to really be diving in to looking at thermodynamics of liquid mixtures to see what information they can provide. Until then, take care.